Okay, we'll continue the discussions on mathematical foundation for industrial engineering. Next, we will discuss about continuation of our previous week materials, in which we call it survey of matrix theory. Here are some agenda that we're going to discuss in this particular slides. So first, about solving linear equation system using Cramer's rules, and then what is eigenvalue and eigenvectors, and then similarity transformations, and then metric diagonalization, as well as the eigenvalue properties. Before I start with those materials, I think I would like to recommend several videos that I think um, very inspiring. Um, these videos were very good at giving the explanation of these materials that we're going to discuss in more illustrative way. So instead of only formulations and how does it generate it and then what's the concept behind it, the visualization is quite important for some people, especially that if you have the uh, more comfortable with the visualization learning methods that provide visualization inside of it. So I recommend you to check these videos. I provide the links as well as in the later on. I will also give you the links, but pretty much I think it's very good videos, so please make sure you check about it, as well as this one, which also talk about the Cramer's rules, which we are going to discuss uh, in about a moment, uh, so that you will have more understanding when we start discuss about the Cramer's rules later on. Okay, first, before we talk about the Cramer's rules itself, of course, we need to talk about the several foundations that we may need to have in order to understand the formula that we're going to explain in the Cramer's rules. The first concept, which also we already discussed last week, is about the determinant of a matrix. So what is a determinant of a matrix? The determinant is a scalar value that can be calculated from the element of a square matrix. Remember, a square matrix that have the same um, number of um, rows and column. So that's we call a square matrix. It can be 2 by 2, 3 by 3, 4 by 4, and so on. So it is often denoted as here, like this one, a determinant, or in or replacing the determinant with straight line brackets, like this one. So those we read it as a determinant of matrix A. And it is used in the various branches of mathematics, including linear algebra and as well as calculus. So it's good to have those understanding of determinants before we discuss about how Cramer's rules were going to be able to discuss later on. Okay, now in these slides you can see an example of a determinant of a 2 by 2 matrix. Okay, determinant of 2 by 2 matrix is very simple. You can calculate it by multiplying the elements of the main diagonals. So the elements of the main diagonal will be the top left and the bottom right. You multiplied it like this one. See, this multiplied by this. So A, let's say if we represent that the top left is A, bottom one is D. So A multiplied by D, then you minus it or subtracting it with the products of the element of the other diagonal. So now this is the top right, which is called P here, multiplied by a C or multiplied by P here. Okay, bottom left multiplied by the top right. Okay, CB. So here you can get a scalar value which you call a determinant of a 2 by 2 matrix. Okay, let's move on with an example in which for a determinant of a 2 by 2 matrix of this matrix A, which has the elements of um, 5. Okay, if you give the uh, symbols here, this will be A, B, C, and D. Okay, the value of A will be 5, B will be 2, C is -6, and then D will be the 3. Okay, and then determinant of matrix A, or you can have this one, the single straight line bracket, will be equals to A multiplied by D minus C multiplied by B, or B multiplied by C. Okay, so here we have like, what is A? 5. What is B? It will be equal to 3 minus, or subtracted with C, which is -6 here, and then D will be equals to 2. So you have this one, this will be 15, and then minus and minus here become plus, so it will be 15 plus with 12, so you got 27. Okay, for a larger matrix like this one, a 3 by 3 matrix, so the determinant is calculated using a process called expansion, which involves adding up to the products of a certain submatrix. There are different methods of expanding the determinant of matrix, such as Laplace expansions, which use the element in the first row or column, and the cofactor expansion, which use the determinant of submatrix formed by deleting one row and one column. So this one is an example of a determinant of a 3 by 3 matrix. So you can use you can augment it, the like mirror the matrix in the middles, and then you can multiply the entries from the down of the first diagonals to the corresponding up of the right sides. Meanwhile, the second one will be from the up left to the associated diagonals to the bottom right. So here's are the examples, so you can follow these explanations, but I will not try to explain in so much details because you should be able to follow this one up after those explanations earlier. So here's is the example. So after you got this formula in the by expanding those metrics and following the particular corresponding formulations generated by those expansions, and then you can apply it for the 3 by 3 formula matrix here. Okay, I will not try to give you the detailed calculations, but here you can try it by yourself. But in summary, determinants of a metric is a scalar value, like you see here. It's a scalar value like 6, or previous also scalar like 3 or something. So it can be calculated from the element of a square matrix. Remember, a square matrix have the same number of rows and column, like this one 3 by 3, previous one 2 by 2, which can be various methods such as Laplace expansion, cofactor expansions, and it can be used in various branches of mathematics such as like linear algebra and as well as calculus. Okay, now that we understood how to calculate a determinants of matrix, we can move on to the solving linear system equation using Cramer's rules. So Cramer's rules is a method for solving systems of linear equations with 2 or more variables, okay, with the same number of equations as well the same number of variables. For example, these equations, we have 2 linear equations. So first is the equation number 1. The second one, we call it equation number 2. And then if we see how many variables do they have, we have first variable equal to x, second variable is equal to y. So the same number of equations, we have 2 equations, and then the same number of variables, 2 variables, x and y. Okay, so normally in a linear equation system, we are trying to solve those linear equation systems by trying to find the value of the variables that able to satisfy the equations, okay, without violating it. So let's say here we want to try to find x and y. right? So the the Cramer's rules is given by this particular formula. For example, if you want to find variable x, you can calculate it by calculating the determinant of x and determinant of d. Now, which is you already learned about determinant earlier. Now the question is, what is determinant of x? Determinant of x is states that where the determinant of x is the determinant of a matrix, so you have a matrix here, obtained by replacing the columns of the coefficient matrix with the constants of the right side of the equation. Okay, to make it clear, you need to first convert this into a matrix system. For example, here, this equation, if you convert it into a matrix system, you will have it something like this. A1, and then B1, A2, and then B2. Okay. Okay, and then you will multiply it by x and y, and then it will be equals to C1 and then C2, right? Okay, let's go back to the formula of how to find the value of x. X, you can calculate it by having the determinants of the metric of the coefficient here. Coefficient x and y will be this one, right? A1, B1, A2, B2. So you replace the column of the coefficient matrix from the right hand side. So this one, the column that corresponding to the x is the first column here, A1 and A2. So you will replace the first, this one, A1, A2, with the right hand side of the coefficient on the constants on the right hand side. So A1, A2, you replace it with C1, C2. You got determinant of a matrix of C1, B1, C2, B2. So here. And then you divide it by the determinants of the matrix of the coefficient. So here. So you have this one, A1, B1, A2, B2. Okay. And then by calculating this, you will have a scalar value, and those scalar value will represent the value of x. Okay, and then after that, now we have the x being calculated. Now you can calculate the y as well using the Cramer's rules. This one, the formula is pretty much similar. Dy divided by d. Dy is what? The determinants of a matrix in which the particular columns of those matrix coefficient were replaced by the right hand side of the constants. Okay, so here we instead of changing the A1 and A2 like previous one when we calculate dx, now we calculate dy by replacing the B1, B2 with C1, C2. So you have here determinants of A1, C1, A2, C2 divided by what? D. D will be the same with the previous matrix that we used. A1, B1, A2, B2. Okay, pretty much straightforward. And then for a 3 by 3 matrix, it's the same way. Just replace the particular column for those variables with the right hand side of it. Okay. Okay, now that we understood the theory, and then let's move on to give you some example. Here we have a linear equation system in which we have the number of the equation here, number 1 and number 2, two equations, and then we have two variables, x and y. So exactly the same with the previous example, but the number of the coefficient will be different. And then to solve this one, we can use the Cramer's rules, in which the first steps, of course, we convert it to the matrix system. We will have the 12 and then 3, and then 2, and then minus 3 here, as well as the right hand side will be equals to 15 and 13, right? So the formula of calculating, if you want to solve this one, you need to you actually want to find the value of x and y, right? And then according to Cramer's rules, we can find the x using this formula. Okay, and then this formula, the dx is equal what? Is equals to, we replace this one, right, with the right hand side of the coefficient in the right hand side, right? So it will be 15, 3, 13, and then 3 and minus 3. Then you calculate the determinant of this one. And while d will be equals to the original coefficient, will be equals 12, 3, and then 2 and minus 3. Okay, and then you calculate it here. This one, okay, to calculate determinants, I hope you still remember the dx will be equal to 15 multiplied by minus 3, and then minus 13 multiplied by 3. So basically it will be equals here minus 45 minus 39, and then the below here d will be equals to 12 multiplied by minus 3 minus 2 multiplied by 3. Okay, so here will be 36 minus 36 minus 6. So you have minus 84 divided by minus 42 will be equals to 2. So the value of x will be equals to 2. Okay, next. Now what about y? Y will be, right, instead of replace the here 12, 3, 2, minus 3 with the right hand side here, the 15 and 13. Instead of replacing the first column here, we're replacing the second column, okay, for the dy. So you will have 12, 2, and then 15, 13 for the dy. Meanwhile, the d will be still the same, 12, 3, 2, minus 3. Okay, and then you calculate the determinants of these two matrix. Here is the following calculations. I will not go in details, but basically you will find the value of y will be equals minus 3. So here you need to indicate that, okay, x will be equals to 2, y will be equals to minus 3 for this particular linear equation system. Okay, next will be another example, but I will leave this one for you to do it at your convenience times. Try to implement this particular theory that I already explained, and if you want to stop the video, stop it here and then continue it later on after you finish understood those materials. Okay, after you finish practicing those Cramer's rules, actually now I want to introduce you a little bit different topics, but we will still discuss this in the class, in which we actually need to learn about a software called MATLAB in order to help you make those calculations easier. Okay, later on, along with the class goes on, I will always try to embed several application of those calculations. Instead of doing it manually, we can use this software to calculate it. So I recommend you to see this video, a rough introduction to MATLAB. It is very straightforward. You can practice along with seeing this video, so that I will not create another video for you to learning those MATLAB for the start or the introduction to MATLAB. But in short, I will explain a little bit. Okay, MATLAB. Well, actually, it's a short for Matrix Laboratory. It's a programming language as well as a software environment. So the programming language called also MATLAB, and then the software environment also for numerical computation, visualizations, and as well as programming. It is developed and maintained by MathWorks, which is widely used in academia and industry for a wide range of tasks such as analysis, modeling, and simulations. MATLAB main strengths are powerful built-in mathematical function. So like previously we learned about determinants, they have those embedded built-in mathematical function for calculating determinants. We don't have to multiply it and then minus those particular values in the matrix by manually. They have built-in function. And as well, its ability to work with matrix and arrays. So it's very convenient to be used for our learning purpose in this class. So it is also has a wide range of toolbox. Toolbox means like functions and clauses embedded in one particular set, which are a collection of specialized function and tools for specific tasks, such as signal processing, control system, and image processing, but we don't really handle those in this particular class. And then another thing is that MATLAB is interactive environment, which allow the user easily write, debug, execute code. So it is also include a number of built-in plotting and visualization tools, so making it easy to create graphical representation of data and results. So that overall, MATLAB, I can say, is a powerful and versatile tools for a wide range of tasks in engineering, science, mathematics, and it is widely used in academics and industrial and development. So it is good to study these tools. I hope to see you able to use it at least for like a simple task. Okay, move on with the materials now after those MATLAB discussion. Now we will discuss eigenvalue and eigenvectors. So if you need a more representation, more visuals explanation about this, go check the videos that I recommend at the earlier of this particular materials. So now move on from my side. The explanation will be like this. So in linear algebra, an eigenvalue of an eigenvector of a square matrix A, so you can calculate eigenvector and eigenvalue of a square matrix. Eigenvalue would be a scalar, and factors, okay, which respectively will satisfy these equations on the right hand side of the PowerPoint. So here, so A multiplied by V will be equals to lambda multiplied by those V factor. So lambda will represent the eigenvalue, V will represent the factors. Okay. So the eigenvalue represented by the factor by which the matrix A stretch and shrink the eigenvector in a given directions. A matrix can have one or more eigenvalues. So a matrix that satisfy these formulations can have sometimes more than one even eigenvalue. So they are useful in variety of fields, including physics, engineering, and computer science. For example, in a system of differential equations, if the matrix represents coefficients of a derivative, then the eigenvectors of the matrix are the factors in direction of the solutions. In image processing, eigenvectors are used to represent dominant direction of an image. So, but that will be for another discussion. For now, you just need to at least have it in your mind. So, eigenvalue will be a scalar that represents the factor by which a matrix can be stretched and shrink to the eigenvector given direction. So you have a matrix, you want to expand it or shrink it in a direction represented by a factor, then those will be the eigenvalue. Okay, so that's why we have these formulations. Okay, for this formulation, if you well, okay, let me go back a little bit. So if you go to that particular videos that I recommend previously, maybe it will explain to you, hey, it may be awkward to have, okay, this one, if you move to the left hand side, you will have this new formulation, a multiplied by phi minus lambda multiplied by phi. Sometimes it's awkward to have, this one is vector multiplied by vector minus scalar multiplied by vector. So you can replace this lambda multiplied by phi by having it become lambda multiplied by I, okay, and then yeah, this one, a multiplied by phi minus lambda multiplied by identity matrix multiplied by phi, and then you can take this one out, the phi out, so lambda multiplied by I multiplied by identity matrix factors. Okay, so basically if you have two sides like this, if you want to make this one equal to 0, you should have either lambda multiplied a multiplied by a minus lambda multiplied by I identity is equal to 0, or the phi is equal to 0. In this one, since if we want to have a vector with direction, the value will be not 0, so you want to find a value where a minus lambda multiplied by identity matrix will be equal to 0. That would be the corresponding eigen value. Okay, next, one example. For example, the exercise sometimes like, okay, find the eigen value and eigenvectors of this eigenvalue. Find the eigenvalues and then the representing eigenvectors for this particular matrix. Okay. First, to find the eigenvalue, remember that the eigenvalue from the previous formula, you can have it by having the a minus the determinants of a minus lambda multiplied by identity matrix will be equal to 0, right? And then if you expand this formula, a minus a will be 0 1 0 1 1 0 1 0 1 0 1 0 1. This one will be a, right? A. And then the identity matrix will be equals to 1 0 0 0 1 0 0 0 1. This one called identity matrix. And then if you multiply lambda with this identity matrix, so we will get lambda 0 0 0 lambda 0 0 0 lambda. Okay, and then if you subtract a with this matrix, lambda multiplied by I or identity, you will get this matrix. Okay, 1 minus lambda 0 1, right? And then 0 minus 0 0, 1 minus lambda 0 1 0 1 minus lambda. Okay, now you calculate this determinants. I know it's difficult. You can use the tools that I introduced in earlier using MATLAB or another tools available in the internet. Then you will come up with this formulation. Then in order to have this formulation equal to 0, you will have a value of lambda equals to 0, equals to 1, or equals to 2. Then these were the associated lambda, or we call it the associated eigenvalue for this particular matrix. So now you have one answer. Oh, we have the eigenvalue for a matrix A will be equals to 0 or 1 or 2. For each particular eigenvalue, you can find the eigenvectors. Okay. Now, if you want to find the eigenvectors, okay, you need to select one of these eigenvalue. For example, now we select eigenvalue of 0. So you input here the eigenvalue of 0. So a minus 0 multiplied by 1, so it will keep equals to a, multiplied by v1, okay, v1 here, and then you want it to equals to 0, okay, then this will be the particular eigenvectors for those particular eigenvalue. So with eigenvalue equal to 0, the eigenvectors will be equals 1. Okay. Now imagine that you have v1. Okay, now we want to find the v1, right? 1 0 1 0 1 0 1 0 1. Now you have it here. Let's say this one will be a, b, and c. Okay, 0 0 0. Okay, here from this one, if you multiply this, so you will have a plus 0. Okay, see, so this one a plus 0b plus c equals to 0, and the second one is 0a plus b plus 0c equals to 0, and then you get here a plus 0 b plus c equals to 0, right? So now you have the associated b will be equals to 0, right? B equals to 0. Okay, and then a plus c is equal to 0. Okay, so implies that there is a free variable which you can be either a or c. If you letting a is equals to 1, then c will be equals to minus 1. Okay, consequently the eigenvector related to lambda equals to 1 is that, okay, here if you have 0 is equals to b, yeah, and then you will have 1, and then this one will be minus 1, something like that. Okay, okay, that's about eigenvalue and eigenvectors. Now just very quick introductions about similarity transformations. I will not explain this one with examples. You can find it in the books for the examples. So basically, a similarity transformation is a type of linear transformation that preserves the eigenvalue of a matrix while replacing its eigenvectors. Okay, preserve the eigenvalues of the matrix while changing its eigenvector. So it is a transformations of let's say if you have a matrix A, n by n matrix, and a non-singular matrix S, an n by n matrix, and suppose that you will have a S inverse multiplied by A multiplied by S will be equals to another matrix called B. Then we can say B has been obtained through a similarity transformations of A. Okay, and that matrix A and B are similar. Similar matrix have the same set of eigenvalue, so A and B will have the same set of eigenvalue under this similar transformation. Okay, next, matrix diagonalizations is a process that transform matrix into a diagonal matrix. So if you want to transform a matrix to a diagonal matrix, meaning that all of its diagonals, okay, will all of its diagonal entries should be equals to 0. Okay, sorry, I mean like all if its diagonal matrix will be equals to the eigenvalue of it. Okay, so when you have here matrix n by n and it has the eigenvalue of lambda 1, lambda 2, lambda 3, and so on, and a linear independent factor v1, v2, v3 until vn, which it will create the matrix P, okay, n by n. Okay, so if you multiply the P inverse with A and then multiply it again with the P, we will have a diagonal matrix of it in which it will consist of the eigenvalue of those particular matrix. Okay. Okay, I think if you want to try again later on, you can try. Okay, if I have P, we have v1, v2, v3 is equal to this one, and then you multiply the P inverse. Okay, you calculate the inverse of this multiplied by A and then multiplied by P, you will get the diagonal matrix, which consists of the eigenvalue of those particular A matrix. Okay, I think that's for eigenvalue, eigenvector, and matrix diagonalization. Here's for closing several eigenvalue properties that you can learn about. First is the determinant of matrix is the product of its eigenvalues. Second, eigenvalue of a lower triangular matrix, upper triangular matrix, and diagonal matrix are the diagonal entries of the matrix. And then third, similar matrices have the same set of eigenvalues. Fourth, eigenvalues of the symmetric matrix are all real. There is no imaginary numbers there. Every eigenvalue of an orthogonal matrix A inverse equal to A transpose has an absolute value of 1. Okay, I think that's all for these materials. Thank you very much for listening.